us about 3D scanning of turf houses, a project he's been working on for a while now. And welcome, yes.
Yeah, thank you. Thank you so much for having me, and thank you for everyone who's watching now or later on. My name's Kathryn. I'm a PhD student here at the university, and I'm here to talk about how the 3D scanning that I've been doing is part of a wider project that's kind of an attempt to future-proof the past, so to better conserve Icelandic turf houses. The overall takeaway from today is that the 3D scanning is a way of combining digital technologies with museum conservation to support the future of the Icelandic turf tradition. We're looking specifically at the timber frames in turf houses with the 3D scanning. So we're looking at better understanding the structural behavior of the houses, and by better understanding the structural behavior, we hope to be able to better conserve them in the future. This is a project that's done in partnership with the National Museum, the University of Iceland, and we are very thankful to have funding from RANIS for the project. A quick overview, it's split into 3 parts. So first we're going to talk about what is 3D scanning, what do we do, how does it work, what is it used for. Then we'll talk about the 3D scanning that I've been doing in turf houses here in Iceland. And finally, we'll talk about the Icelandic turf tradition. So what is the turf tradition? Basically, why are we studying what we're studying? Why is it important? And how does this project fit into that in a wider context? Diving right in. So 3D scanning is a way, of capturing the physical world around us in a digital form to create a 3D model. And this can range from tiny objects to entire buildings or even cities for urban planning, cave systems. There's a huge variety of sizes. Models can include color or texture, but they don't necessarily have to. The 3 most common types of 3D scanning are laser scanning, photogrammetry, and structured light scanning. And we're using LiDAR, which is a form of laser scanning, and we'll come back to what that is in a couple of slides. First, I wanted to show what 3D scanning can be used for and what I find most interesting about it. 3D scanning is used in a huge number of fields. This first picture here is an Orthodox cathedral in Ukraine. This is part of a project called Backup Ukraine. Hi. And this is a project where just people, usually just using their phones, are scanning different monuments or important sites of cultural heritage that are at risk due to the conflict and the war. And this is a way to preserve cultural heritage. And we're seeing an increase in the usage of 3D scanning in this way in conflict zones and in areas that are at risk for natural disaster and climate change. So 3D scanning is a very important part of preserving cultural heritage all over the world in this way. Some of my other favorites, so other fields include engineering, manufacturing, healthcare, entertainment, architecture, construction, education, museums, and cultural heritage. If you look at the image in the top left corner, this is a screenshot from a website called Artec. They're actually the company that manufactures the scanner that we use and the software as well. This is a 3D scan of a suit of armor that has been uploaded into the software and is being scaled down to put into a video game. And this is not an uncommon way to use 3D scanning. I believe there's an Icelandic video game called Isle of Winds that is 3D scanning objects from the National Museum to put into the game. So it's an extra level of historical accuracy if that's your thing, and it's my thing, so I think it's very cool. To the right, here's an example of how 3D scanning can be used in healthcare. It's used to make prosthetics more comfortable. It helps get a better fit. Also, if you're scanning something that needs to be symmetrical for the face, for example, a 3D scan can help make it look more realistic as well. So there's a ton of cool applications in healthcare. Bottom left, we see a long-distance 3D scanner in a tunnel. This is closer to what we're doing. So these kinds of scans in tunnels or cave systems, mines, etc., those are often used for displacement monitoring. And that just means we're looking for displacement or movement in what we're scanning. The bottom right corner is kind of a funny coincidence. I ended up talking with someone who works in a museum in Berlin a couple of weeks ago about increasing accessibility in the museum space. And one of the projects that they're doing is 3D scanning a beetle. So you can kind of see in that picture, the bottom left, that black bit is the actual size of the beetle. They 3D scanned it and then scaled it up to 20 times its size. And this is done for people with visual impairments, to be able to better explore the shape and the texture of the beetle. 3D scanning can therefore be used to improve accessibility, but it's also useful for everyone because we as museum visitors wouldn't be able to see or feel the texture if we were just looking at the beetle behind a glass case. So we can also use 3D scanning to better understand the world around us. If we're looking at this closer to what we're actually doing in historic buildings, 3D scanning is incredibly popular in historic buildings as a non-invasive capture method to document conditions and help with preservation or conservation efforts, restoration projects, research, and long-term planning. It also creates a digital collection that is more accessible and interactive than blueprints or drawings would be on their own. And again, here are just some of my favorite examples. The top left is, of course, Notre Dame. This is a 3D scan done in 2010 by an architectural historian named Andrew Tallon. And this was kind of a fun project, but it ended up being incredibly important for restoration efforts after the fire in 2019. Next to it is the Hill House. So this is a house under Historic Environment Scotland. It's a historic house built in, I believe, 1904, and there are some fun parallels with Iceland and Scotland. This house is concrete, and their climate conditions are quite similar to what we experience here. So as we can maybe guess, they have very similar problems with damp, wetness, mold, all of that. What they have done is combined 3D scans of the house with moisture and thermal surveys to map out the water entry and the direction the water moves when it's in the house. And they're using this as part of a conservation project to better care for the house in the long term. Finally, on the bottom, so this is getting even closer to what we're doing, there has been work done using 3D scanning to monitor displacement in wooden structures. This is a picture from a 2015 study in Taiwan using 3D scanning to measure structural displacement in the 17th century wooden temples. They're doing this so once they identify a certain degree in tilt in the structures, then that particular structure is prioritized for a more immediate repair. This is the closest that we found to what we're doing in the turf houses. There are a lot of differences between these structures and turf houses, and to our knowledge, no one has done the 3D scanning for displacement monitoring in a turf house yet, so we're applying this methodology in a new way. Now, back to LiDAR. So LiDAR stands for light detection and ranging. You can also say laser imaging detection and ranging. These terms are interchangeable. LiDAR is a mapping technology that uses laser light to measure the distance to a target surface to create a 3D map. It's calculating depth and distance, and it's used for larger scale projects in engineering, construction, urban planning, architecture, mining, things like this. So you would use this type of scanner for the larger projects and a different, much smaller scanner for the beetle that we were looking at a couple slides ago. It calculates the distance to the nearest surface by logging the time it takes for the laser beam to return from the object that's being scanned to the scanner. And here we have a visual aid of what this looks like. So this is taken again from Artec's website. This is their explanation of how their LiDAR scanners are working, and this is again what we're using. So this image on the left, this can be understood as the scanner. On the right, the opaque body is just referring to what's being scanned. So in our case, the opaque body is the inside of a turf house. A laser is emitted from the scanner, reflects back off of the object, and allows the scanner to measure the reflected light to determine the shape and dimensions. And this is then used to form point clouds, which can be processed into 3D models. And those 3D models can be used in any number of applications, like all of the things we were looking at a couple of slides ago. We are using an Artec Ray scanner owned by MSHL. It's the largest 3D scanner in their collection. It's a long-range 3D scanner, and its range is between 1 and 110 meters. We're usually scanning between 1 and 3 meters distance from the walls. There is an accuracy of 0.7 millimeters when scanning from 10 to 15 meters, and it's again a 360-degree capture to give us this 3D model. So you can see this image also from Artec, scanning vertically and horizontally as it's going around. Now, I hope that we understand a little bit more about what 3D scanning is, how it works, what it's used for. Now we're going to go into scanning in the turf houses. So we're scanning in 4 different locations, 2 in the north, Laufás and Grenjaðarstaðir, and 2 in the south, Keldur and Árbæir. These locations account for differences in climate between the north and the south, and also differences in materials used and the layouts of the houses themselves. To give you a better idea of what I mean by the differences between them, here we have 4 rooms that we're scanning. So going from left to right, we have the kitchen in Keldur, the Dúnhús or down house in Laufás, the kitchen in Árbæir, and the last picture, the scanner is sitting in the front entryway of Grenjaðarstaðir. So we can see a huge difference between the interiors. Keldur on the far left, the interior is just stone and timber. Next is levels, which is primarily turf with a stone base and timber used in the frames and the roof. Then Augbeit is quite interesting. 3 of the walls are very thin layers of turf with stone, and then the wall that the scanner, or that's behind the scanner, is just wooden paneling. And finally, Grenjurstaðir is entirely wooden paneling inside where we're scanning, at least. Now, we're scanning because we know the houses are moving. People have reported it who work closely with the museums. In many cases, it's also visible to the naked eye. What we don't know is the how and the why. So we're looking at if this movement is seasonal, if it's fluctuating or one directional, if it's related to weather patterns, if it's part of the natural decay of the wood, how much it's moving, at what rate is it moving, and if it's moving the same between the different houses. Here we have some examples of movement. So in the far right in Grenjurstaðir, there's a very obvious tilt in the wooden structure. That's a very visible thing. On the left, this is taken in Laufás, and the tilt is less visible, but it's still there, particularly when you're looking at passageways and door frames. And so I should also say we're focusing on 3D scanning today, but understanding the movement of the timber frames can't be done in isolation. There are a lot of other factors that contribute to it. One of the other things we're doing is looking at modeling hydrothermal behavior in the roofs, because the turf roofs, the turf walls, all of that also affects the timber frames. And here we see an example of a mitigating factor. The middle image was taken also at Grenjurstaðir. There's very obvious damage to the exterior of the wall. Above this, there's also damage to the turf roof. This damage has created quite a large hole. You can actually see part of the timber frame inside through the hole. And this hole will allow more moisture to get inside. It changes relative humidity and temperature and accelerates decay. So this is another thing that we're looking at in addition to just the 3D scans alone. This is an image of a rendering created in Artec Studios, that software that we're using. This is a compilation of 4 or 5 scans, and the wall that we're looking at in this rendering is the same wall that's behind the scanner in the image up in the top right corner. What we're doing with this is that we're placing thumbtacks in the wooden frames, and then we're measuring movement of the thumbtacks in between scans. So we're aiming for 3 to 4 scans per year. These thumbtacks are serving, therefore, as a fixed point within a room where almost everything is moving. The floor is moving, the walls are moving, the roof may be moving, the timber frames are moving. There's a lot of movement, so having a set fixed point allows us to measure this more carefully. The renderings are great. I think they're very pretty, but I'm a bit biased. They do support having a digital collection of 3D scans, but we're much more interested in point clouds and not the renderings themselves. Point clouds are a collection of points with X, Y, and Z coordinates that describe each point's precise location within the scan. These 2 images are actually the same point cloud, but open in different softwares. So on the left, this is done in Artec. Artec Studio is great for a lot of things, but we want to have much more detail than the point cloud in Artec can provide. So we are using an open source software called Cloud Compare. It's specifically designed for 3D point cloud editing and processing. And again, this is the same point cloud. You can see the level of detail on the right is much more than on the left. And Cloud Compare allows us to compare these fixed points. For a number of reasons, we do not yet have 2 complete scans of a single room. An interesting discussion, but not one for right now, I think. So we've not been able to successfully prove that this works in the turf house, but we have been able to prove that it works in a more controlled environment. It's a bit dark, I apologize for that, but if you can see this sort of black object in the center of the 2 objects or images on the left, this is just the lid for the tripod for the scanner. In the offices at the National Museum, I put it on a bookshelf, took a scan, moved it 1 centimeter to the right, took another scan, imported those to Artec and then Cloud Compare, and I was able to measure the displacement or the movement of the lid for the scanner. Now I moved it 1 centimeter, the difference was measured at 7.6 millimeters, so there is an error margin of about 2.4 millimeters. That's okay for now, I think. It shows that it is possible to measure small-scale displacement in the way that we hope to do in the turf houses. So fingers crossed for this coming autumn and winter. Now, coming back to the Icelandic turf tradition, so why we're doing this, basically. Turf houses in Iceland represent the vernacular architecture of the country, and vernacular architecture just refers to a local or regional type of building using traditional materials, methods, and resources from the surrounding area, where knowledge and techniques are passed down from generation to generation. What's especially exciting about the turf tradition, I think, is that no two houses are the same, and even within the same house, different materials and methods may be used. So there's a huge variety of turf houses. I think when you're visiting them, it's also exciting because each one is so unique, and you can visit the same one again and again, and depending on the time of day and the year, you're going to have a totally different experience. Turf houses represent an incredibly important architectural tradition that has evolved and been in active use from the 9th to the 20th century. At the turn of the 20th century, roughly 90% of the population still lived in turf houses, but that rapidly declined going into the 20th century. The last people that lived in turf houses did so in the 1990s, which is incredibly late. The 4 houses that we're looking at were lived in until between 1936 and 1964. And 1964 is still very, very recent. So this means that the turf tradition and living in turf houses still exists in living memory. And this is very different from other countries that also had turf architecture because it died out many, many years before, centuries before often in those countries. So this means that Iceland still has working knowledge that is being actively passed down between generations. And that means that Iceland has become a place where people from all over the world come to learn about turf houses. And that is a huge variety of research being done. Some of it is building, some of it is humanities-based. There's a ton of cool stuff happening. The turf tradition also represents an incredibly important form of tangible and intangible forms of cultural heritage. While a lot of work has been done, there is still a lot to do, and that's what we're trying to do here. Turf houses also feature in, I think, very wildly interesting discussions, both past and present, about Icelandic nationalism, the independence movement, politics, identity, healthcare, colonialism, tourism. Almost anything you can think of that's popular in Iceland today, you can somehow link turf back. I recommend trying to do it. Unfortunately, though, turf is often still dismissed, it's not very respected, and it has a poor reputation. And this is one of the things we're trying to address. Turf houses are awesome. I think they're very cool. Again, I'm biased, but they don't deserve the poor reputation that they have, and this is one of the ways we're working to improve their reputation. In a wider context, in terms of the research that we're doing, as I've said, we're trying to fill a gap in the field of research with the structural behavior. We're also documenting structural conditions every time we do a site visit, and that includes the 3D scans, also photographs, and just written records of measurements and things like that. We're working, one of the long-term goals of the project is to create a remote monitoring system for the National Museum or any museum working with turf houses to be able to better identify and prioritize repairs. In an ideal world, you would be able to fix everything as soon as it's damaged, but we don't live in an ideal world. There are a lot of turf houses that need a lot of repair, and those repairs are expensive. So by being able to better prioritize and identify things that need repair, it will make for more efficient conservation. I also mentioned we're doing hygrothermal modeling, so we're looking at the hygrothermal behavior of the roof, and in combination with the 3D scanning, that will make up the remote monitoring system. And finally, we are trying to highlight the Icelandic turf tradition both in Iceland and abroad. And here are some of my favorite pictures of the work that we've been doing in different parts of the country. So in all of these ways, this is how we're combining digital technologies like 3D scanning and museum conservation to preserve the past for the future. Thank you so much.
Oh, thank you. Oh, questions?
Yeah, maybe a quick one. You say at the beginning when they were combining 3D scanning and like moisture sensing, so basically do they do, I mean, as far as you know, because that's not your project, but or if you were to do it, would it be like, doing some moisture sampling and recording at specific times and scanning at the same time? Yeah,
exactly.
It's combined. That's not the tool that does that.
No, they're and it's even when you're doing 3D scanning of a huge house, it's different types of 3D scans that then have to be compiled, and then they had people going with sensors to do the readings, and then that was separately added in. It's a huge project, but a very interesting one.
Super interesting.
I guess the obvious question is, why haven't you been able to scan more than one
We've
scan.
had so many opportunities to learn.
Yeah.
The first is the temperature. So I think the lowest range that the scanner can function is 5 degrees.
Okay.
Inside the turf house is a bit above 5 degrees, but when I was talking with the tech team, they said that long-term exposure of 6-7 degrees is probably enough that it makes it stop working. We've also been recommended to get new SD cards, which we did. Originally, the sensitivity settings on the scan were too high. So Jon Bergman, who's a 3D scanning guy in Iceland, he was able to help us realize that we should lower the sensitivity settings. That has helped a lot. I've sent the logs when the scanner has crashed to Artec. They've also recommended recalibrating the scanner, but that would require sending it abroad, which is a whole other kind of can of worms. We were, though, in our last trip to Teeter, able to get our first complete scan there. So the temperature conditions were right, we had the new SD cards, and we were just lucky. So yeah, a combination of things, I think, yeah.
It was mainly kind of technical
Yes.
issues that had come up with the scanner and the environment and just how to make this thing
Exactly.
work.
Yes.
Yeah, yeah. So this winter is going to be kind of important then?
Yes,
To get
very much so,
back
yeah.
in? Yeah.
Fingers crossed.
Yeah, but we're working on, as Kathryn is showing, also just developing the method. What are we going to do with the scans? Even though we don't have the scans, we've started developing the method of how we're going to compare them when we get them. So we're not stuck. We're just waiting for the next time that we're going to scan and using the time to develop our method in the meanwhile. So using tripod lids and in libraries.
Yeah, exactly.
Yeah. So one kind of net question: if when you have more than one scan of the same environment, the same room, or the same house, how do you go about the comparison? Is it, are there kind of just tools ready that can compare the dots in the cloud, or how does it work?
So you just have to kind of help the software align the scans, which is relatively simple to do, and then you have to show which points you want to fixate on. So you do that separately. So you align them, choose the points, and then align them again, and then there's a tool that allows you to measure the distance between those 2 points.
Okay, yeah. So that's it's a bit like when you put a layer on the on the mesh, you need to find the fixed points, and then it does the rest.
Yeah.
Okay.
Cool.
Are you any way related to this turf fiction people?
No. Sigurjón in turf fiction, I worked with him in my master's before I started my PhD. I am very into turf fiction, but it's a completely separate project, yeah.
What is turf fiction?
It's Sigurjón, who's still heading the MA in design,
I think so, yes.
He's
still
but they've had a long-term project with Teeter also here about just not turf fictions, but looking at the turf house as a living body, almost.
Yeah, like this giant organism.
Exactly.
Is how they have described it. It's a really cool project.
Yeah.
But we've been talking with them a lot, but it's different enough to what we're doing that it's a totally separate project. Yeah. But a really cool one.
On the broader cultural aspect, so this is kind of an engineering project in a way. So you're looking at how the mood change during the year, and this has an effect on what you can do to preserve them and do things. But then you mentioned just kind of big cultural questions like nationalism, etc. Do you self, or how do you relate to that concretely in this project?
Not so much concretely in this project. I like to discuss it because I think a lot of the times people are so quick to dismiss turf as not important and it doesn't matter anymore, but it has been kind of foundational in a lot of ways of getting to where Iceland is today. And so I just tried to kind of tie in that it's an important part of the past and it should be preserved and studied and not just forgotten and left behind or left to decay. Yes, Sigurjón has a couple of really interesting articles about turf houses and politics and nationalism as well.
My father grew up in a turf house, so it's not.
Yeah.
It's not a problem.
No, not at all. It's been really fun to speak to people who grew up in turf houses.
Yeah.
And like, you know, all of the problems with concrete houses that we're having today, it's not so dissimilar from the turf houses. So I think they have an undeserved bad rap.
Yeah, they're basically moist, so it's not gonna. That's not a problem.
Is the intuition that they are moving for other reasons? Because isn't every building more or less moving in some way, like, you know, with humidity and whatever, like timber houses and stuff like that. So do you have like a hunch of are they moving for other reasons than other buildings, or is it like do you want to find out?
Yeah, I don't have a hunch.
Yeah.
I'm excited to find out. I don't know if you have a hunch.
So we wonder if we have a combination of seasonal fluctuation, which is also what you find in a timber house, and differential settlement, which would then be caused by probably some moisture problem somewhere.
Yeah.
But we don't know exactly. But the hunch is that we probably have an inclined line that is going the same way all the time, but with a fluctuation around it due to the seasons. So that is sort of like what we think, but we don't know yet.
Not with every in architecture, there's a lot of discussions around this idea of responsive buildings, or that would be more in tune with the environment and take into account the climate change and all these things. So I think that's very interesting.
And climate change is another topic where Kathryn didn't have time to go into, but like we're seeing the houses in the north maybe decaying faster now because they're built for a climate that is now changing, and it's worse for them than it is for the buildings in the south because they were a little more built for it, like they're more built for these very high seasonal fluctuations, a lot of rain and things, whereas the northern houses are built for more stable, cold winter with not a lot of rain. So we are seeing that as well.
And I think there's also a difference in like the seasonal movement and in some of the houses where the movement is to a point that it's just going to permanently damage the structure in the long term.
With differential settlements where you're really just like going the same direction all the time.
So it's not like contracting and then drying and stuff.
No. It's just going in.
There's been a lot of really interesting things that have been tried in the past to keep them from moving, like up in Leros. I don't remember the year, but sometime in the late 20th century, they put iron bars around all of the buildings, hoping that would help, and it did the kind of opposite of that, because when one started really moving, it pulled
the rest.
Yes, exactly. So there's been a lot of different things tried as like a response to a problem. We just need to learn more about the problem before we try something else.
You are doing that.
Where is this? Is it Denmark or something? They have this like seagrass roof tradition, you know, and they have to water the roof of the house like regularly to make sure it's still alive instead of maybe.
Have to do that here in the summer if it gets too hot and too sunny, and sometimes also trim the grass as well if it's getting too long.
Caring for the building.
It is like the living organism, like turf fiction in a way.
Can I ask about the models? Because you are doing these high quality scans. You're doing it to kind of compare the points, etc. But you end up with scans of buildings that may be of interest to a lot of people. So how are they? Where do you store them? How are they going to be accessible to?
The National Museum will have a copy of everything, and then I think how that's shared is kind of up to them.
We haven't discussed this in detail with the museum, what we're going to do in the end, but we will first have to sort of be sure that we have good quality scans and then know what we're working with. But we haven't finalized sort of like if there's going to be any data sharing or what we're going to do. So that's sort of still in the making. But I know that's common. that people like, when they're done, they're like, now we're gonna share this somewhere where everyone can see it, but I don't know what the policies of the museum are and how they see it.
No, I mean, they have a page on Sketchfab where they have some objects, you know,
Yeah.
shows and things, but they're kind of much more smaller scale, not that much as far as I remember. So it's a question if this kind of, if we will have it on the whole 12 house in a full 3D model someday.
Maybe.
Kentut, the entirety of Kentut has been scanned.
And it's
I don't-
accessible somewhere.
Yes, I don't know if it's Sketchfab, but
Yeah, but maybe somewhere else, yeah.
Yes, the one that's been protected with the, so to say, what they built is glass
No.
structure and so on.
Kelton is one of the houses here.
So yeah, you have there.
what is the glass structure?
What's the name of this thing? The architects that did it just got some prize. I forgot the name. Anyway, it was more like an archaeological site.
Ah, okay, yeah.
Oh, you mean Stink?
Stunk.
Yeah.
Yes.
Okay, no, so it's been.
It's like changed because Stink is an archaeological place, and it was such that you could just go there and you can walk around it. It was like open for everyone, and it wasn't really a museum in that sense. You just go there, and it had been built. It was a house that you went inside, but it was sort of like a frame that had been built over it. But then they took down that frame and they built a new frame, and now it's such that you're sort of you walk into a balcony, you watch. You cannot just walk around in an archaeological site anymore. You're sort of more like a visitor, like looking down into it, and they've done it very beautifully. It's very well done. Yeah. And it's better than it was before because it's glass, so you actually have light going in there. Before it was just corrugated steel, and it was really dark in there. Yeah.
Cool.
So this is really cool.
Yeah.
How much have you done the project?
I have just finished 1 year out of 3. Ambitious 3.
Ambitious,
Yes, we'll see how long it ends up taking.
Two winters to go.
Yes, yeah, 2 winters to go, exactly.
So, thank you very much. It's been great.
Yes, thank you.
Yes.
Thank you.
Thank you. And thank you.